Hello everyone, this is Pragya Sahu, PMRF scholar at Department of Chemistry, IT Kanpur. Today I will take the second lecture of this thermodynamics chapter. So let us start. So we will quickly go through what we studied in the previous lecture. So as I told you, that the thermodynamics is a branch of physical chemistry that deals with the study of energy changes during chemical and physical processes. So here basically we study the transformation of energy. For example, we have any matter such as fuel and we put it in a car engine. So the combustion of the fuel will produce heat, which can be used for mechanical, electrical, or other kind of works. So this is basically a transformation of energies. So in thermodynamics, basically we studied the transformations of energies. So during this transformation of energies, you will notice that the energy is not getting lost. It is converting from one form to another. This is only the first law of the thermodynamics that I will discuss in the next lecture. So, which is basically that the energy can neither be created and it cannot be destroyed. It can be transformed from one form of energy to another. Okay. So, so we have studied some thermodynamic terms, the system and the surroundings. So the system is that part of the universe under study, and the surrounding includes everything else. For example, we have this is a beaker, this is a conical flask, okay, containing, let's say, water. So this water will be our system. Okay, we have to study something on this system. Okay, now the system is your water, and except this, everything will be your surrounding. So except your system, everything part of the universe will be your surrounding. Okay. So to study the flow of energy during a chemical reaction, we need to distinguish between a system, the small, well-defined part of the universe in which we are interested. Such as, let's say, there is some chemical reaction is taking place in this conical. Okay? So this is our part of interest. Okay, so we are going to conduct our study on this system. So rest of this will be its surrounding. Okay, let's now this container will be our surrounding. So the mixture of chemical substances that undergoes a reaction is always the system. And the flow of heat can be from the system to the surrounding or vice versa. Okay. So if we take the system and the surrounding, so the whole will be called as universe. So our universe will consist of the system and the surrounding. Okay. So the system is that part of the universe we are interested in studying, such as chemical reaction inside the flask, as I already mentioned. So based on this, the system can be of three types: an open system, a closed system, or an isolated system. Okay, so an open system is that system which can exchange both matter as well as energy with its surroundings. Okay, for example, a pot of boiling water is an open system. Let's say we are boiling water. This is a flask containing water, okay, and we put it on a burner, okay, so flames will come. So now the energy is getting transferred from this burner to this flask, okay. Now, so this is the exchange of energy, okay. Next, if let's say if this is the boiling water, okay, this is the boiling water. Now vapor formation will take place and vapors will be get exchanged with the surroundings. Okay, so this kind of system is called an open system where the both matter as well as energy is exchanged within the system and the surroundings. Next is our closed system. So in closed system, what happens? Only energy can be exchanged, but no matter can be exchanged with the surroundings. So let's say we have in these days we have this ready-made dinner kind of thing, okay. So they come in this sealed pouch, okay, and we have to boil them to eat it basically. So this sealed pouch of ready-made dinner, that is we have, when it is dropped into a pot of boiling water, the whole system will be called as closed system. Let me tell you how. That here the thermal energy from the boiling water is getting transferred to the sealed pouch, okay. So only, but the pouch is closed, sealed, okay. So the contents of the pouch will not come out, okay. So if it is not spilling, then your matter is not getting exchanged with the surrounding, okay. This kind of system we call it a closed system. Next is we can also explain this with an example. Let's say we put a lid on a saucepan, okay. So putting a lid on the saucepan makes the saucepan a closed system. So let's say this is a saucepan, okay, and we put a lid, okay. This is a lid and we put a lid, okay. Now this system is closed, okay. So this kind of system will be called as closed system because here no matter can be exchanged from the saucepan, okay, because the lid prevents the matter from entering the saucepan and leaving the saucepan, okay. Next is the isolated system. So basically an isolated system neither exchanges heat nor matter with the surrounding, okay. For example, an insulated thermal flask containing hot coffee will be called as an isolated system, okay. Let's say this is your thermal flask, okay. So it contains some coffee, okay. So the wall is now the wall is insulated, which means now energy cannot be transferred from the system, okay. As the flask is closed, okay. So neither our matter is getting transferred, okay. So here neither matter means whatever your flask contains, let's say a hot coffee, so neither your matter is getting exchanged with the surrounding, neither the energy. If you are keeping hot coffee, your coffee will be hot, but in actual there is not a truly isolated system doesn't exist, okay. So As stated earlier, that an insulated thermal containing hot coffee approximates an isolated system, but eventually, as no truly isolated system exists, the coffee cools as heat is transferred to the surroundings. Okay, it will not remain hot for a longer time. Here, I have given example. Okay, so this is a cup of tea. Okay, so here the tea is hot. Okay, the tea is hot, so energy is getting exchanged with the surrounding, and the matter, as the lid is, there is no lid, the matter is also getting exchanged with the surrounding. Okay, here if we put a lid on your cup of tea, so here energy is still getting exchanged, as this is not an insulated wall, but here matter cannot be exchanged. Next is this your thermal flask. So here neither energy, as the wall is insulated, nor your matter, as the lid is closed, can be exchanged. Okay, so this kind of system will be called as an isolated system. Okay, next we studied the boundaries. So boundaries are basically the imaginary or real separation between the system and the surrounding. Okay, so let's say this is your conical flask and some chemical reaction is going on. Okay, some mixture is there. Okay, so now, so this is our system. This mixture is our system. Let's say we are carrying out this reaction in this container. So this is the container, and we are carrying out a reaction in this conical flask. Okay, so this is our system. As I told earlier that except system, everything will be your surrounding. So here the container will be your surrounding, and the boundary. Okay, the separation, the boundary which the boundary of the conical flask, this will be your boundary. It separates your system and surrounding. Okay, so this will be your boundary, means the wall of the conical flask. The conical flask will act as your boundary. Okay, so based on this, there are three types of boundaries: permeable boundary, semi-permeable boundary, non-permeable boundary. Okay, so let us first see permeable boundary. In permeable boundary, it says that here exchange of matter as well as heat. Okay, so if a boundary permits the exchange of matter as well as heat, then it will be called as a permeable boundary. Let's say, for example, this is your beaker containing a reaction mixture. So here this beaker will act as the wall of the beakers will act as your boundary. Okay, here exchange of matter can be done. You can see that the beaker is not closed, so exchange of matter can be done, and heat can also be done. Okay, so this boundary will be called as a permeable boundary because it is allowing the exchange of heat as well as matter. Okay, a semi-permeable boundary is that boundary which only allows the exchange of heat but not the matter. Okay, now if we close this beaker with a lid, Okay, this is a lead. Okay, now that we have closed, exchange of matter cannot be done, but heat can be exchanged in this case. So this hole, let me change the color. So this the lid and the wall of this beaker will act as your boundary in case of semi-permeable boundaries. Okay, this kind of boundaries only allows the exchange of it, but doesn't allow the exchange of the matter. Okay, next is this non-permeable boundary. So in this kind of boundary, so there is no exchange of matter and nor any exchange of heat. Okay, the wall of your thermos flask. Okay, this is your thermos flask. Okay, so this thermos flask doesn't allow the heat as well as matter. Both cannot be exchanged from the system and the surrounding. So the wall of this thermos flask will be considered as your non-permeable boundary. Okay, so its wall will act as a non-permeable boundary. Okay, so in conclusion, three types of boundaries are there: permeable boundary, semi-permeable boundary, and non-permeable boundary. This kind of boundaries which doesn't allows the exchange of matter, and this kind of system are called adiabatic system. Okay, next, the state and state functions. So the state of a system is a complete description of a system at a given time. Okay, including its temperature, pressure, and the amount of matter it contains, as well as its chemical composition and the physical state of the matter. Okay, so basically what it means to say that let's say we have a system. Okay, change the color of the pen. We have a system where we have taken a water in this flask. Okay, so what is the temperature? So let's say 25 degrees Celsius. What is the pressure? Let's say 1 bar. What is the volume? Let's say 0.25 liter. Okay, so this is the description of a system at a given time. So at this time, what is the temperature of the system, pressure, volume, or what is the concentration of the system at this time? Okay, so at a point it is defined. Okay, so this is called the state of the system. And a state function is a property of a system whose magnitude depends on only the present state of the system, not its previous history. Okay, so a state function is a property of a system whose magnitude depends on only the present state of the system, not on its previous history. So temperature, pressure, volume, and potential energy are all state functions. So basically it means that it only depends on the final state of the system. Okay, it doesn't matter how it has reached that final position or final state. If that is the case, then that will be called as a state function. Okay. So as mentioned that temperature, pressure, volume and potential energy are all state function. Temperature, pressure, volume and potential energy as well as density. These are all state functions. Okay. So all these are state functions. So that, for example, the temperature of an oven is independent of however many steps it may have taken for it to reach that temperature. Okay, let's say we have an oven. Okay. It is at some 75 degrees Celsius. Okay, so doesn't matter how this temperature of 75 degrees Celsius has reached, the temperature will be same. Okay, it is so the temperature at this time is 75 degrees Celsius. It doesn't matter how it has reached or what path it has taken. Okay, so therefore the temperature is your state function. Okay. Next is your pressure. Similarly, the pressure in a tire is independent of how often air is pumped into the tire for it to reach that pressure. Okay, suppose we have a tire. Okay, what is the pressure of the tire? Okay, so it doesn't matter how many times air has been pumped into the tire to reach that pressure. Okay, the pressure of the tire will be same. So pressure is also a state function. Similarly, the volume of the air in the tire, the volume of the air in the tire. Okay, so the final volume. What is the final volume of the air in the tire? So it doesn't matter how this volume has reached. Okay, so this is the volume of the tire. Okay, so therefore it is also as a state function. It doesn't matter how many times the air has been pumped into the tire. It will be this. Okay, the volume depends only on the final state. Okay. Okay. As mentioned, that density, temperature, pressure, volume, and potential energy all are state functions. Okay. Heat and work, on the other hand, are not state functions. Okay, because they are path dependent. So, as I mentioned earlier, that the final decides what. Okay, here let's say, okay, for example, we have this car on the top of a building. Okay, so a car is sitting on the top level of a parking garage. So it must have some potential energy. This is the car. It must have some potential energy. Okay, so this car sitting on the top of the parking garage has the same potential energy whether it was lifted by a crane, set by a helicopter, driven up or pushed up by a group of students. Okay, so the amount of work expended to get it there will differ depending on the path chosen. Okay, so let's say this is the path A. So the amount of work done to get this car from here to here at this position will be different to the amount of work done when this man pushes this car upwards to the top and to this final position. Okay, so this is path B. Okay, so the amount of work done will be different and they chooses a different path. Okay, so work is a path function. Okay, if let's say if the student decides to carry the car to the top of the ramp, okay, they would perform a great deal more work than if they simply push the car up the ramp. Okay, so here, whether they followed path A or path B, the car will be here only. Okay, so no matter which path they choose, the potential energy of the car is the same. Okay, so basically, no matter what path they choose, the potential energy of the car will be the same. Okay, so the potential energy is not depending on the path chosen. So when a property doesn't depend on the path chosen, it only depends on the final position, initial or final position, then what will it be called? It will be called as a state function. Thus, we can conclude that the potential energy is a state function. Okay. Okay. So for next example, let's say a person has to climb up to this point. Okay. So let's say person A chooses path A. Okay. And person B chooses path B, this blue one. Okay. So obviously this A will take a longer time to reach this point. Okay. While the person second will take a shorter time to reach this point. But their final destination is the same now. Their final destination is the same. So even though path 1 is longer and more winded than path 2, both paths lead to the same destination. In this case, although the two paths are different, their final change in altitude is the same. So hence they have this same state function value of altitude. Okay. Basically, this path is longer than this one, but their destination is the same. Okay. So here we can say that although the two paths are different, their final change in altitude is the same. Okay, the change in altitude is the same. So here altitude. So here they have the same state function value for the altitude. Okay, the key points. Okay, state functions only consider the initial and final state of a system, not the states in between. Oh, okay. So state functions, let us understand with this example. Let me change the color of the pen. Okay. So this is the initial position of the person A and this is the initial position of the person B. Okay. This is the final position. So the let's say the potential energy. Okay. So the potential, the altitude here, the altitude will be same for both. Okay, so the altitude will be, the value of altitude will be same. Okay, so the it only depends on the initial and final state of the system, not on the path they followed. Okay. So let's say for another example, in a lab setting, if the volume of container A, which has an initial volume of 1 liter, okay, let's take another example. Okay, I will just add a slide. Okay, let me just add another slide to make this point more clear. Okay, so now we have the slides. We can explain it in a better, we can understand it in a better manner. So let's say in a lab, we have a container A, which contains 1 liter of, say, water. Okay, let me expand it. So we have a container. Okay, this is the container A. Okay. It will be better if I take a container like this. So this is your container A. Okay, it contains 1 liter of, let's say, water. Okay, and we have a piston over here. Okay, okay, let's just take another example. We have this container A and another container B. Okay, so A has an initial volume of 1 liter and immediately expands to 2 liter. So the net change will be 1 liter. Firstly, it is 1 liter, then it changes to 2 liter. Okay. Now the change between these are 1 liter. Okay, the net change is 1 liter of water. Okay, now this is container B. Okay, its initial volume is 1 liter. It also contains 1 liter of water, and it goes from 1 liter to 5 liter. Okay, let's say now this is containing 5 liter of water. Okay, now it again, the volume of the container again changes from 5 liter to 0.5 liter. Again it changes from 0.5 liter to 2 liter. Okay, so but this was your initial volume. Okay, now this is final volume. So the net change is 2 liter minus 1 liter. Basically 1 liter. Okay. So although the containers A and B differed in their volume change paths, but because the initial and final volumes of the container are the same, their net changes is the same. Hence, volume will be considered as a state function along with other functions, other properties I mentioned earlier. Okay. So volume is the state function. Why state function? Because it doesn't depend on the path followed, but depends on the initial and final state of the system. Initial and final state of the system. Okay. So in this way, what we studied is that the temperature, pressure, volume and potential energy, these are all state functions, as they depends only on the initial and final state of the system, not on the path they followed to reach that state. Okay. So now we studied state functions. So this is now we will study what is path function. So a path function, as the name suggests, that it will depend on the path. Okay, so a path function is a property whose value depends on the path taken to reach that particular state. Okay, so basically it considers the journey or process undergone by the system. Okay, so for example, work. Okay, as mentioned earlier, that work depends on the path taken. Okay, so for example, we have to reach this place. Okay, this is our final position. Okay, and this is our initial position. This is our final state. This is our initial position. So we can choose this path to reach this position. We can go through this path to reach this position, or we can take this path, or whatever path we can take. Path C, path B, path D. Okay, so to reach this station, this position, we can take either of the path. So the amount of work or energy will be different in each case. Okay, so we can see that this path A will take the minimum energy. Okay, while this is the longer path. Okay, so it will take the higher amount of work to reach that position. Okay, so in this way, work will called as a path function because it depends on the path followed, not on the initial or final state. Okay. Next is heat. Change in internal energy, chemical work, electrical work, all this kind of energy are path function because they depends on the path. So in conclusion, the change in their value between two states, that is we denote it with delta, is the same regardless of the path taken. Okay, and for the path functions, the exact path matters. Okay, the path followed matters over here. Okay, and the different path may result in different values for the change. Okay, so that's for today. So we will in next class we will study internal energy as a state function, and we will study more about work, heat, and many more state path functions. Okay, after that I'll start with first law of thermodynamics. Okay, thank you.